Ranger 2, prepare to detach.
What? No! No! Cooper!
3.
Cooper, what are you doing?
Newton's third law. You gotta leave something behind.
Hello, 8. So this question, structured question on stationary waves. So figure 1 shows a stretched string driven by a vibrator. The right-hand end of the string is fixed to the wall. The stationary wave is produced on the string. The string vibrates in 2 loops. So what we got here, that's your L. And in this case, L is actually equal to lambda because it's the second harmonic. So, okay, so state the physical conditions that are necessary for a stationary wave to form. So the first obvious thing, you need to have 2 waves traveling in opposite directions. Okay, now whether it's 2 separate waves or whether it's a wave, an incident wave that's reflected back on itself, which it is in this case. Now, it says for a stationary wave. It didn't say for this one in case, but you could have easily said that the incident wave and the reflected wave travel in opposite directions. Now, the other thing they need to do, they need to be coherent and have the same frequency. Okay, what does coherent mean? It just means constant phase relationship or constant phase difference. I'll just put it in brackets. And what same frequency, that means they have the same wavelength, wave speed and amplitude. So that's it's pretty much the whole criteria or description of a stationary wave. So explain how you know the wave on the string is transverse. So if you look at the oscillations, or the oscillations are 90 degrees, or the vibrations are 90 degrees to the direction of travel. So the oscillations are 90 degrees perpendicular to the direction of energy transfer. Okay, let's move on to the next one. So compare the amplitude and phase of oscillations of A and B on the string. So you're going to have to measure. So the amplitude for this one is there. This amplitude, clearly smaller. Okay, so amplitude of A is larger than B. And what else do we know? If you just look at the arrows I drew, A is facing upwards. Okay, and B is facing downwards, so that's 180 degrees, or antiphase, or the rate of phase. So antiphase, probably shouldn't use that, just give the number. Antiphase, it's 180 degrees, or it's pi. Okay, let's move on to the next bit. So the length of the string is 1.2 meters, so 1.2 meters must be lambda. So that's equal to lambda. Okay, and the speed, so I'll give you V. All right, so from that, I should be able to work out frequency, question mark. So there's only one formula you need for this, so V equals F lambda. And in this case, we're trying to work out F, so it's V over lambda. Put your numbers in, 6.2 over 1.2, which in this case is 5.2 hertz. Okay, don't forget that you've got the other formula for V, which is indirectly on this. It's not on the spec itself, but you should know it's indirectly. V is equal to root T over mu. Okay, and you've seen that in the formula F equals 1 over 2L square root T over mu. Okay, so F equals 1 over 2L square root T over mu is just a variation of F is V over lambda. Okay, so let's move on then. So the frequency of the vibrator is triple, sketch the new shape. Well, if you get 2 for that frequency, if you triple it, you're going to get 6. Okay, so you're going to try and draw 6. Oof, it's going to be interesting. So I'll go draw 6 loops. Let me just find the middle. It's probably easier. And then this might not be, oh, it's not bad actually. See if I can mimic that this side. Okay, it'll do. Okay, so there is sketch of, okay, so this is a new shape. Show on your diagram 3 points P, Q, and R in phase. Now, what you can do, you could actually do 3 points in one loop, okay, because these will all be in phase. If you put one of them there, that's incorrect, because if these are going up, let's say, this is going down. Okay, this point is actually going down, so that would be out of phase. What you could also have done, you could have put them one here, one here, one here if you wanted. Okay, because these are all going up, these are going up, and these are going up. In fact, you could have done it, so you could have done these 3 points. Okay, so you could call them PQR, or you could have done these 3 points. I'll put P dash, Q dash, R dash, or again, any variations of those. Just remember, adjacent loops are in antiphase. Okay, so that's how you'd answer that.